Every atom in your body should have already collapsed. The electrons inside you carry a negative charge. The nucleus pulls them in with a positive one. Classical physics said they had to spiral inward and crash. All matter, gone in less than a second. But here you are, solid, real. Something stopped it, and the answer cracked physics open at its foundation. We are going inside the electron, the tiniest confirmed piece of matter in existence, a particle so strange it exists in multiple places at once, passes through solid nuclei, and holds every atom in the universe together through a rule that says the more you corner it, the harder it fights back. If you enjoy the ride, subscribe and leave a like. Let's go. Picture every atom in your body detonating at once, every chair, every wall, every molecule of air collapsing into itself in a fraction of a second. That was the prediction. A genuine, mathematically sound prediction made by some of the smartest people who ever lived. The physics was clean, the logic was tight, and it said that all matter in the universe should have destroyed itself before anything had a chance to form. The year was the late 1800s. Scientists had just started piecing together what atoms actually looked like on the inside. They knew atoms contained positive charges and negative charges. They knew opposite charges pulled toward each other, and from centuries of studying electricity and motion, they had a set of rock-solid rules that described how charged objects behave when they move. Those rules worked perfectly. They explained lightning, they predicted how magnets behave, they described the flow of electricity through a wire with stunning accuracy. And then they were applied to the atom. The result was a catastrophe on paper. The negative charge inside every atom, the electron, was assumed to be orbiting the positive center the same way a planet orbits the sun. That picture made sense at the time. Gravity keeps planets in orbit. Electrical attraction could do the same for electrons. Neat, orderly, stable. Except one of those rock-solid rules said something ugly. Any electric charge that moves in a curved path radiates energy outward. A planet is not electrically charged, so it keeps orbiting forever. An electron is. So every single time it curved around the nucleus, it had to bleed a little energy away as radiation. A little energy lost means a slightly smaller orbit. A smaller orbit means a tighter curve. A tighter curve means more energy lost, faster. The spiral accelerates. The electron falls inward. Scientists calculated that the whole collapse would take less than 100 millionths of a second. Every atom ever. Gone. Sit with that for a second. The same equations that correctly described every electrical experiment ever run in a laboratory were screaming that the atom was impossible, that you are impossible, that the chair under you and the air in your lungs should never have existed past the first instant of the universe. Physics had two options: ignore the math, or accept that something was deeply fundamentally wrong with the picture of the atom everyone had agreed on. Nobody ignored the math. The hunt began for whatever was missing. Something had to be stopping the electron from falling. Some force, some rule, some principle that the old equations had never accounted for. And the search for that missing piece would take 3 decades, burn through the careers of the best minds on Earth, and produce the strangest, most unsettling branch of science ever created. The old model of the atom, that clean little solar system with electrons looping around a bright central nucleus, was elegant. It was satisfying. It felt true, and every second it continued to exist was a mystery nobody could explain. Physicists started asking harder questions. What is the electron actually? Where does it sit? How does it move? They assumed they were about to find a small correction to their equations, a minor tweak to an otherwise solid theory. What they found instead rewrote the rules of reality from the ground up. And it started with one man, a glass tube, and a beam of glowing light that curved in a direction it had no business curving. The solar system model of the atom felt like a gift. It was the early 1900s, and scientists had just confirmed that atoms had a dense, heavy center packed with positive charge, Ernest Rutherford fired tiny particles at a sheet of gold foil thinner than paper and watched most of them pass straight through, but a few bounced almost backward. That backward bounce was the clue. Something tiny and extremely dense sat at the heart of the atom. Rutherford called it the nucleus. So now they had a picture. Dense, positive nucleus in the center, light, negative electrons somewhere around the outside. The natural next step was to imagine the electrons looping around the nucleus, just like planets looping around the sun. Rutherford himself promoted this idea. It had visual logic. It had intuitive weight. It made atoms feel like miniature galaxies, orderly and permanent. Every science textbook in the world eventually printed that image, and the image was a quiet disaster waiting to be noticed. The problem was not the shape of the orbit. The problem was what electrons are made of. Planets have mass and gravity. They carry no electrical charge. So when Earth swings around the Sun in its curved path, nothing about that curve costs it any energy. It keeps going indefinitely. Electrons are electrically charged. That changes everything. When a charged particle moves in a curve, it sends out waves of electromagnetic energy. Radio antennas work on this exact principle. Drive an electric charge back and forth, and it broadcasts radio waves outward in all directions. An electron curving around a nucleus was doing something essentially identical. Every fraction of a loop, it was radiating energy away from itself. Each burst of radiation meant slightly less energy inside the electron. Less energy means a shorter range. A tighter orbit means a sharper curve. A sharper curve means more radiation, faster. Scientists ran the numbers and found the spiral would not be gradual. The electron would drain itself to zero and crash into the nucleus in under a 10 millionth of a second. The most stable-looking model of the atom in history carried a built-in countdown to annihilation. Every atom should have collapsed long before stars formed, long before Earth cooled, long before the first molecule of anything assembled itself into something we might one day call life. The solar system model, the one being printed in textbooks, the one taught to students as the structure of matter, predicted total universal collapse before the universe was old enough to build anything. Rutherford's model had another problem too, one that did not involve death spirals. It could not explain color. When you heat a gas of hydrogen and look at the light it gives off through a prism, you see a handful of precise, sharp lines of color. Red, blue-green, violet, specific shades, identical every time, no matter where in the universe the hydrogen comes from. An atom radiating energy continuously as it spirals inward should produce a smooth, unbroken rainbow of light, every color blending into the next. Hydrogen produced sharp lines instead. That detail was a clue nobody could explain yet. The solar system model could account for none of it. It predicted a smooth spectrum and instant collapse. The atom produced sharp colors and lasted forever. The equations in the experiment were pointed in completely opposite directions. Niels Bohr looked at Rutherford's model, looked at those sharp spectral lines, and decided the rules of orbit needed to change. His solution would be radical, and it would plant the first seed of something even stranger. Niels Bohr was 27 years old when he decided to break physics on purpose. He had studied Rutherford's solar system model. He understood the death spiral problem. He also understood the color line problem, and he made a decision that had no justification in any existing science. He declared that electrons were simply not allowed to orbit at just any distance from the nucleus. Only certain specific distances were permitted. In between those distances, the electron could not exist. There was no reason for this. Bohr just looked at the data, looked at the sharp spectral lines of hydrogen, and worked backward to a rule that would produce them. His rule was that electrons could only occupy fixed, specific energy levels, like rungs on a ladder. The electron could sit on one rung or the next. but never in the empty air between rungs. When an electron jumped from a higher rung to a lower one, it released a burst of energy as light. The specific gap between the rungs determined the specific color of that light. Different gaps produced different colors. The sharp lines of hydrogen matched Bohr's calculations with unsettling precision. The model worked spectacularly. Hydrogen's color lines lined up exactly with the predictions. But Bohr could not explain why the rule existed. He just imposed it. He had essentially said, electrons are forbidden from spiraling inward because I say so, and here is proof that this matches reality. That is an extraordinary thing to put into a scientific model. A rule with no mechanism, a law with no reason. The physics community accepted it anyway because nothing else came close to matching the data, and buried inside Bohr's compromise was the most important unanswered question in atomic science. Why are only certain orbits allowed? What is actually preventing the electron from sliding to any distance it wants and spiraling down into the nucleus? The answer to that question would arrive a little over a decade later, and it would shatter the remaining comfort of the solar system image entirely. The key lay in understanding what an electron actually is. Bohr had been treating it as a tiny solid object flying in a circle. That picture, it turned out, was wrong in the most extreme way possible. In the 1920s, a French physicist named Louis de Broglie asked a question that seemed ridiculous at the time. If light, which everyone thought was a wave, could sometimes behave like a particle, could a particle like an electron sometimes behave like a wave? He worked out the mathematics and found that every moving electron has a wavelength, a real physical wavelength. The electron was not a ball traveling a circular path. It was more like a ripple wrapping around the nucleus. And ripples have a rule. They only sustain themselves cleanly when the loop fits a whole number of wavelengths, like a guitar string that only vibrates at certain notes. If the loop is the wrong size, the wave cancels itself out. Bohr's forbidden orbits suddenly had a reason. The allowed orbits were the ones where the electron wave fit perfectly around the nucleus without destroying itself. The forbidden zones were simply places where the wave would have cancelled out and vanished. The solid little ball of an electron was already dissolving into something wave-like and spread out. And that transformation was about to get far stranger. In the autumn of 1897, J.J. Thomson was alone in his Cambridge laboratory, staring at a glass tube. The tube had been pumped almost completely empty of air. At one end sat a metal plate connected to an electrical source. When Thomson switched the current on, something invisible shot out from the metal plate and travelled the length of the tube, hitting the glass at the far end and making it glow a faint, eerie green. Scientists called this a cathode ray. They had been studying these glowing tubes for decades. The debate was about what the ray actually was. Some said it was a wave, like light. Others said it was a stream of particles. Nobody had settled it. Thomson placed 2 electrically charged metal plates on either side of the tube and switched them on. The glowing beam bent. It curved toward the positive plate and away from the negative one. That meant whatever was in the beam carried a negative charge. Waves do not respond to electric fields like that. The beam was made of particles. Then he placed a magnetic field around the tube. The beam bent again. By measuring exactly how much the electric field bent it and how much the magnetic field bent it, Thomson could calculate the ratio of the particle's charge to its mass. The number he got back was extraordinary. The particles in the beam were roughly 1,800 times lighter than the lightest atom known, the hydrogen atom. Thomson had just found something smaller than an atom. In 1897, scientists believed atoms were the smallest things in existence. The word atom comes from the ancient Greek word for uncuttable. The assumption was baked into the name. Thomson had just cut it. He called his particle a corpuscle. The name did not stick. Within a few years, the world had settled on the term electron, a word coined earlier by an Irish physicist named George Stoney to describe the basic unit of electrical charge. What Thomson had actually demonstrated was that matter had structure inside it. Atoms were not solid, uniform, uncuttable spheres. They contained pieces, negatively charged pieces that were dramatically lighter than the atom itself. And if negative charge was in there, positive charge had to be somewhere too, to balance it out. Thomson proposed a model he called the plum pudding model. He imagined the atom as a soft, spread-out blob of positive charge with electrons embedded in it, like raisins in a pudding. It sounds absurd now, but it was the best fit for the data available at the time. That model would be dismantled 14 years later, when Rutherford fired particles through gold foil and found the nucleus hiding at the center. But Thomson's real contribution was simpler and more powerful than any model. He had proven that a particle smaller than an atom existed. That matter went deeper than atoms. That physics had a whole new layer to explore beneath the surface of chemistry. The electron was real. It had measurable properties. And for the next 100 years, the question of what it actually was, at its deepest level, would keep getting harder to answer, because the more precisely scientists tried to pin the electron down, the stranger it became. By the middle of the 20th century, physicists had a new tool, the particle accelerator. The idea was simple and violent. Take a subatomic particle, accelerate it to a significant fraction of the speed of light, aim it at another particle, smash them together and catalogue whatever flies out of the wreckage. The debris from the collision reveals what was inside. This method worked brilliantly for protons and neutrons. Smash a proton hard enough, and it splits apart. Out come smaller particles called quarks, 3 quarks per proton, 2 per neutron. Inside those quarks, physicists found hints of even deeper structure, particles called gluons holding the quarks together with tremendous force. The proton turned out to be a complicated, busy little object packed with moving pieces. Physicists turned their accelerators on the electron. They smashed electrons together at energies far exceeding anything needed to shatter a proton. They looked for fragments. They watched for debris. They measured every angle, every energy level, every particle that emerged from the collision. Nothing came out. No smaller pieces. No internal structure. No evidence that the electron contained anything inside it at all. Every collision produced whole electrons bouncing away or electrons transforming into other fundamental particles through known quantum processes, but never a broken electron. Scientists repeated this at higher and higher energies. The answer stayed the same. The electron appears to have no interior. Physics classifies it as an elementary particle. Elementary means it sits at the absolute base of the structure of matter. It is not assembled from smaller components the way a proton is. It simply is what it is, all the way down, with nothing smaller beneath it. This creates an immediate problem that physicists have never fully solved. If the electron has mass, and it does, where does that mass live? Mass usually means stuff packed into space. A proton has mass because it contains quarks and gluons bouncing around inside a defined volume. When you try to apply the same reasoning to the electron, you hit a wall. The electron appears to be a point particle, a location in space with no dimensions. 0 width, 0 height, 0 depth. A mathematical dot, packing real mass and real electrical charge into a space of exactly 0 volume, produces an infinite density. Mathematics breaks down completely at that point. The equations produce answers of infinity, which is a signal that something in the model is wrong. Physicists call this problem the self-energy of the electron. It has never been resolved. The current working solution in quantum field theory involves a mathematical trick called renormalization, which essentially subtracts the infinity away using carefully defined procedures. The trick gives correct predictions, but it does not explain why the infinity appeared in the first place. The electron refuses to be simple. Smash it and find nothing. Examine its mass, and find a mathematical crisis. Measure its location and run into a rule that says you cannot. Generations of physicists built careers trying to find a crack in the electron's surface, a hint of depth, a seam where something smaller might be hiding. The electron has not given one up yet. And the deeper scientists look, the more unsettling the picture becomes. When physicists call something an elementary particle, they mean something specific and extreme. A molecule can be broken into atoms. An atom can be broken into a nucleus and electrons. A nucleus can be broken into protons. A proton can be broken into quarks. Each step goes deeper. Each step finds new structure, new pieces, new physics. The electron has no step below it. It sits at the floor. The standard model of particle physics is the most tested scientific theory in human history. It describes every known fundamental particle and every force those particles carry, except gravity. It has been checked against experiments thousands of times. Its predictions match reality to a level of precision that would be like measuring the distance from New York to Los Angeles and getting the answer right down to the width of a single human hair. Within the standard model, particles divide into two families: quarks, which build protons and neutrons and interact through the strong nuclear force, and leptons, which include the electron and do not interact through that force. The electron is a lepton. It belongs to a group of 6 lepton types, 3 of which carry charge and 3 of which are neutral. The electron is the lightest and the most stable of the charged leptons. Its 2 heavier cousins, called the muon and the tau particle, behave almost identically but decay into lighter particles within microseconds or less. The electron never decays. Scientists have never recorded a single electron breaking down into something else under normal conditions. It appears to be completely stable on timescales longer than the current age of the universe. That stability is one of the deep, unexplained facts of physics. There is no known reason why the electron refuses to decay. The muon has the same charge. The muon obeys the same forces. The muon falls apart almost instantly. The electron holds together forever. The standard model accepts this difference without fully explaining it. Every atom in the universe owes its existence to this stability. Hydrogen atoms formed in the early universe still have their original electrons. Stars built from those hydrogen atoms converted them into heavier elements through nuclear fusion. Every carbon atom in your body, every oxygen molecule you breathe, every iron atom in your blood carries electrons that have never decayed, never broken down, never stopped being electrons since before the first stars switched on. The electron is also absurdly light. A proton is roughly 1,836 times heavier. Imagine a bowling ball sitting on one side of a scale. On the other side, you would need to stack 1,836 marbles to balance it. The proton is the bowling ball. Each marble is an electron. Despite weighing almost nothing, the electron carries exactly the same magnitude of electrical charge as the proton. The charge is opposite in sign, negative versus positive, but equal in strength to a precision that has never shown any measurable difference. That perfect balance is what makes atoms electrically neutral. 1 proton, 1 electron, total charge of 0. The match is exact. Nobody knows why the proton and electron, 2 completely unrelated particles built from entirely different stuff, happen to carry charges of identical strength. It is one of the most precise coincidences in all of physics, and it is completely unexplained. For most of history, scientists pictured the electron as a thing, a small object, a speck, a marble. That picture is gone now. Quantum field theory, the most accurate physical theory humans have ever built, replaces the idea of particles as individual objects floating through empty space. Instead, the universe is filled with invisible fields, one for each type of fundamental particle. These fields stretch across the entire cosmos, through every galaxy, every star, every atom, every millimeter of what we call empty space. The electron field is one of these. It exists everywhere, even in regions of space where no electron has ever been detected. The field sits at a resting state, calm, waiting. When energy gets added to the field at a specific location, the field responds. It produces a ripple, a localized vibration, a concentrated knot of energy that behaves from the outside exactly like a particle. That ripple is what we call an electron. Every electron ever measured is not a separate individual object that exists independently from the universe. Every electron is the same field, vibrating in a different location. The field is the real thing. The electrons are its expressions. This distinction is not just philosophical. It has direct physical consequences. Think of the surface of the ocean. A wave on that surface is not an object. It is a pattern of motion moving through the water. Two waves can overlap, pass through each other, combine or cancel, and then separate as if nothing happened. The water itself stays water. The patterns come and go. Electrons behave this way because they are patterns in a field, not objects sitting in space. When two electrons interact, the fields overlap and push against each other. When an electron emits a photon, it is the electron field exchanging energy with the photon field. The particle language we use in everyday physics is a shorthand for these field interactions. One consequence of this picture is immediate and strange. If every electron is a vibration of the exact same underlying field, then every electron is completely identical to every other electron. Same mass, same charge, same spin, same in every measurable way. Not approximately the same, mathematically, physically, exactly the same. Two hydrogen atoms formed on opposite sides of the universe will each contain an electron indistinguishable from the other in any measurement ever devised. No serial number, no individual history, no unique properties. They are the same ripple in the same ocean. This is completely unlike anything in everyday experience. Two coffee cups made in the same factory are similar, but not identical. Microscopic scratches, slight weight differences, tiny impurities in the ceramic distinguish them if you look closely enough. Two electrons have no equivalent imperfections. They are the same thing at the most fundamental level reality allows. The reason physicists are confident this is true is that quantum mechanics produces precise predictions that only work if all electrons are truly identical. Any deviation from perfect identity would show up as measurable errors in those predictions. No such errors have ever been found. The electron is not a particle in the classical sense. It is the universe vibrating in a very specific way, and that vibration has rules about where it can and cannot go that are unlike anything Newton or Maxwell ever imagined. Two objects that are truly perfectly identical in every measurable way raise an immediate and unsettling question. Are they actually two objects, or are they one? This question is not philosophy. In quantum mechanics, it has a physical answer with real consequences for how atoms behave and how matter holds together. Classical physics treats every object as a distinct individual. Two billiard balls of the same size and weight are still separate things. You can track which one is which across time, label them with paint, watch them move. Ball 1 stays ball 1. Ball 2 stays ball 2. Their identities are preserved even when they collide. Electrons cannot be tracked this way. An electron has no label, no paint, no distinguishing mark. When two electrons interact and move apart, there is no physical measurement that can tell you which one was which before the interaction. The question of which electron is which becomes literally meaningless. Physicists built this fact into quantum mechanics as a fundamental rule. When you calculate the behavior of a system of electrons, you must account for the fact that any electron in the system could be swapped with any other without any observable change. This requirement shapes the mathematics, and that mathematics produces something called the Pauli exclusion principle. Wolfgang Pauli worked this out in 1925. His principle states that two electrons cannot occupy the same quantum state at the same time, same location, same energy, same spin direction. All of those match. Impossible. At least one property has to differ. This rule is the reason the periodic table has the structure it does. Electrons fill atomic energy levels from the bottom up, one by one, each occupying a slightly different state. Once a state is filled, the next electron is pushed into a higher level. That stacking pattern determines how many electrons sit at the outer edge of the atom, which determines how the atom bonds with other atoms, which determines all of chemistry. Every molecule you have ever encountered, every drug, every protein, every strand of a genetic molecule, exists in the shape it does because electrons cannot share states. The geometry of chemistry comes from this one rule about identical particles. The Pauli exclusion principle also holds matter up physically. In dense objects like white dwarf stars, where gravity has crushed the material to extreme density, it is quantum exclusion that resists the collapse. The electrons are already packed as tightly as the rule allows. Gravity pushes. The rule pushes back. The star holds its shape not because of any conventional force, but because identical particles refuse to overlap. Remove the Pauli exclusion principle, and matter as we know it stops existing. Atoms collapse. Chemistry vanishes. Stars implode. The solid ground you are sitting on would fall through itself. All of that follows from one strange fact. Every electron in the universe is exactly the same as every other one. And that sameness carries one more strange implication that physicists rarely talk about casually. Some calculations in quantum field theory suggest that all electrons might actually be the same single electron, weaving back and forth through time in all directions simultaneously. The idea is too strange to prove and may never be testable, but it has never been ruled out. In 1927, a pair of American physicists named Clinton Davison and Lester Germer fired a beam of electrons at a crystal of nickel. They expected the electrons to scatter off the surface of the crystal, the way billiard balls bounce off a rough wall. They had aimed a stream of particles at a solid object. Particles bounce. That is what particles do. What came back was an interference pattern. Alternating bands of high-density and low-density electrons spreading outward from the crystal like ripples from a stone, dropped in still water. That pattern only forms when waves overlap and interact. When a crest from one wave meets a crest from another, they combine and make a taller crest. When a crest meets a trough, they cancel and leave nothing. Electrons were producing this pattern. Individual electrons, fired one at a time, eventually built up the same banded structure on a detector screen. Each electron arrived at a single point, like a particle would. But over many trials, those points accumulated into an interference pattern that could only come from wave behavior. The electron was somehow going through both paths at once, interfering with itself, and then arriving as a single dot. This was the experiment that made the wave-particle question impossible to dodge. The electron was doing something that had no name in classical physics. It was moving as a wave of spreading possibilities, exploring all paths simultaneously, and then collapsing to a single location only when it actually hit the detector. Physicists tried to figure out which path the electron actually took. They placed detectors along both possible paths, trying to catch the electron in the act of splitting. The moment they did this, the interference pattern vanished. The electrons started behaving like ordinary particles, choosing one path, arriving at one point, producing no wave pattern at all. Watching the electron destroyed the wave behavior. This remains one of the strangest confirmed facts in all of science. The act of observation changes the outcome of the experiment. The electron seems to know when it is being watched. Not because it is conscious, but because measuring a quantum system requires physically interacting with it, and that interaction collapses the spread-out wave into a definite location. Before the measurement, the electron exists as a smear of probability, many places at once, all paths at once, no definite location. After the measurement, one location, one path, definite. The experiment has been repeated countless times with electrons, atoms, and even large molecules. The interference pattern keeps appearing when nothing measures which path was taken. The pattern keeps vanishing the moment a measurement happens. Every version of quantum mechanics ever developed has to account for this. The result is confirmed. The explanation for why it happens remains one of the most debated questions in the history of physics. The electron does not exist in one place until you force it to. Before that, it is a wave of probability spreading through space, carrying every possible future at once. And that wave has a shape, a very specific mathematical shape that scientists can calculate and predict with extraordinary accuracy. That shape is what keeps atoms alive. Erwin Schrödinger sat down in the winter of 1925 and spent 2 weeks in near isolation. He had taken a book of physics papers to a villa in the Alps, brought a companion whose identity he never disclosed, and when he came back, he had written an equation. One equation. It described how the wave nature of the electron evolves over time, spreading and shifting through space, according to precise mathematical rules. The Schrödinger equation transformed the question of where an electron is into a question of where an electron probably is. Feed it the structure of an atom, turn the mathematical crank, and it produces a three-dimensional map of probability. A cloud, thick in the regions where the electron is most likely to appear, thin in the regions where it is unlikely, zero in certain zones where it physically cannot exist. These clouds are called orbitals. The word orbital sounds like orbit, but the two things are completely different. An orbit is a defined path, a track, like a highway the electron follows. An orbital is a region of space where the electron has a high chance of being found if you look. The electron does not travel around the nucleus. It exists as a probability cloud around the nucleus, smeared through a volume of space without a fixed location until something interacts with it. For the lowest energy state of hydrogen, the simplest atom, this cloud is perfectly spherical, a fuzzy ball of probability surrounding the nucleus, dense at the center, thinning out as you move away with no sharp edge. The electron could technically be found anywhere, even far from the atom, though the probability drops off fast with distance. Here is the visual that makes this real. If the hydrogen atom were expanded until its nucleus was the size of a basketball sitting at the center of a football field, the electron's probability cloud would fill the entire stadium. The electron is not zipping around the sidelines. It is smeared across every seat, every aisle, the field itself, with the highest chance of being found somewhere in the lower rows. The cloud is not the electron moving fast. The cloud is the electron existing in a genuinely undefined location, superimposed over a range of space at once. This is what Bohr's model was missing. He gave the electron a defined track and said certain tracks were forbidden, without explaining why. Schrödinger gave the electron a wave function and showed that the allowed energy levels correspond to wave shapes that fit stably around the nucleus. The forbidden zones are the regions where no stable wave shape is possible. The Schrödinger equation solved the structure of hydrogen's energy levels exactly. It matched the observed spectral lines with perfect precision. It extended to heavier atoms and correctly predicted their behavior. It became the mathematical engine of all of modern chemistry. But it raised an immediate, uncomfortable follow-up. If the electron is a spread-out probability cloud, what happens when you measure it? The cloud covers a huge region, but every measurement ever taken finds the electron in one specific spot. The cloud collapses to a point, one interaction, one location, then the cloud begins spreading again. That collapse is the moment physics becomes philosophically strange. And the man who formalized what the cloud actually was waiting for another measurement to arrive was about to rewrite the rules of what can even be known. Werner Heisenberg was 23 years old, and his face was swollen with hay fever. It was the spring of 1925, and his allergies had become severe enough that his academic supervisor gave him 2 weeks off. Heisenberg went to a small island called Helgoland off the coast of Germany, a rocky outcrop in the North Sea, with almost no trees and therefore almost no pollen. He brought physics textbooks. He barely slept. He was chasing a problem that had been eating at physicists for a decade. The problem was simple to state and impossible to solve with the tools available. Atoms emitted light at specific frequencies. Bohr's model predicted those frequencies almost correctly. Almost. For hydrogen, it worked. For anything more complex, the predictions broke down. Something about the mathematical framework was missing. Heisenberg decided to throw away the pictures entirely. Every model of the atom up to that point had tried to describe what the atom looked like, where the electrons were, what paths they followed. Heisenberg looked at this and decided it was the wrong approach. Nobody had ever directly observed an electron inside an atom. Nobody had watched it move along a path. All of physics could only observe what atoms emitted and absorbed. Spectral lines, energy differences, transitions. He built a mathematical system around only those observable quantities. No pictures, no paths, no positions, just the numbers that experiments could actually produce. The mathematics he invented was strange. When he multiplied two of his quantities together, the answer depended on the order of the multiplication. Multiply A times B, and you get a different result than multiplying B times A. In ordinary arithmetic, 2 times 3 and 3 times 2 both give 6. Heisenberg's system gave different answers depending on which came first. He found this deeply disturbing. He worked through the night, checking his algebra over and over. By 3 a.m, he was certain the mathematics was consistent. He was too excited to sleep. He climbed to the tip of the island's rocky shoreline and watched the sun come up over the North Sea. When he returned to the mainland, his supervisor Max Born recognized the structure of his mathematics immediately. It matched a system that pure mathematicians had studied decades earlier, called matrix mechanics, with no physics application in mind at the time. Heisenberg had independently invented it, trying to describe an atom. Schrödinger's wave equation arrived shortly after. The two approaches looked completely different. One used probability clouds, the other used grids of numbers with no pictures at all. Within a year, mathematicians proved they were identical. Same predictions, different language. But Heisenberg was not finished. His non-commutative mathematics contained a hidden message, a constraint buried in the algebra, a limit on what could be known at all. He found it in 1927, and when he published it, the philosophical consequences landed like a shockwave across the entire scientific community. The limit was not a practical one. Scientists had always assumed that better instruments would eventually allow more precise measurements of anything. Heisenberg's limit was different. It was built into the structure of reality itself, and no instrument could ever overcome it. Werner Heisenberg pulled the hidden message out of his own mathematics and stared at what it said. The result was the uncertainty principle. Its statement is precise, and its consequences are enormous. It says that certain pairs of physical properties are fundamentally linked. Know one of them precisely, and the other one becomes correspondingly fuzzy. The more precisely you pin down one, the more wildly uncertain the other becomes. The most important pair is position and momentum. Position means where something is. Momentum means how fast it is moving and in what direction. In everyday life, there is no practical conflict between knowing both. You can watch a baseball in flight and know its location and its speed simultaneously, to any precision your instruments allow. The uncertainty is purely a matter of instrument quality. Build better instruments, get more precise answers. Heisenberg showed that for quantum particles, this reasoning fails entirely. The uncertainty is physical. Halve the uncertainty in position, and the uncertainty in momentum doubles. Make the position perfectly precise, and the momentum becomes completely unknowable, spreading across all possible values simultaneously. There is no instrument that overcomes this, because better instruments make the problem worse, not better. This is because measuring something in quantum mechanics requires interacting with it. To locate an electron, you must shine light on it. But a photon of light carries momentum. When it hits the electron to give you position information, it kicks the electron and changes its momentum in an unpredictable way. Use shorter wavelength light to get a more precise position reading, and each photon carries more momentum, kicking the electron harder, making the momentum more uncertain. Use gentler, longer wavelength light to disturb the electron less, and the lower resolution of that light makes the position reading fuzzier. Every attempt to reduce one uncertainty increases the other. The trade-off is not a flaw in the measurement, it is a physical reality baked into the nature of waves. Heisenberg's mathematics expressed this as a formula: the product of the uncertainty in position multiplied by the uncertainty in momentum can never fall below a specific fixed number. That number is extraordinarily small. For everyday objects like baseballs, the limit is so far below the sensitivity of any conceivable instrument that it is completely irrelevant. For electrons, confined to the tiny space of an atom, it dominates everything. Now picture an electron being forced into the nucleus of an atom. The nucleus is roughly 100,000 times smaller than the atom. Confining the electron there means shrinking its possible range of position by a factor of 100,000. Heisenberg's principle says that compressing the position uncertainty by that much forces the momentum uncertainty to expand by the same factor, roughly 100,000 times larger. A 100,000-fold increase in momentum uncertainty means the electron's speed becomes wildly, violently unpredictable. It could be moving in any direction at enormous speed. The average energy of the electron in that confined space skyrockets. That energy does not go away. It has to go somewhere. And what it does with all of that energy is the actual answer to why the atom does not collapse. Squeeze the electron toward the nucleus, and it does not cooperate. Every step inward compresses its allowed range of position. And by the rules Heisenberg uncovered, compressing the position means the momentum must spread over a larger and larger range of values. The electron's kinetic energy, the energy of its motion, rises dramatically. The tighter the confinement, the higher the energy. This is called the quantum confinement effect. It is real, measurable, and used in modern technology. Engineers who build quantum dots, tiny semiconductor particles used in television screens and solar cells, exploit this exact phenomenon, make the particles smaller, and the energy levels inside it rise. The color of light it emits changes based on its size, all because shrinking the space forces the quantum energy up. In an atom, this rising energy acts as an outward pressure. Picture a spring compressed in a box. Push the walls of the box inward, and the spring pushes back harder. The quantum confinement effect works like that, except the spring is invisible, made of mathematics, and rooted in the fundamental impossibility of knowing both where the electron is and where it is going. The nucleus pulls the electron inward with electrical attraction. The electron's quantum energy pushes outward with increasing force as it gets compressed. At some specific distance from the nucleus, these two effects perfectly balance. The inward pull of the positive charge equals the outward push of quantum confinement. The electron settles there. That balance point is the ground state of the atom, the lowest possible energy configuration. The electron cannot go lower because falling closer to the nucleus would require more confinement, which would push the energy back up, undoing any gain from the electrical attraction. The atom settles at the energy minimum where the two effects cancel. This is the actual answer to the question that threatened to destroy physics a century ago. The electron does not fall into the nucleus because falling in would cost energy rather than release it. Quantum mechanics makes the nucleus a dead end, not a destination. The classical picture was wrong in a specific way. It assumed that electrons lose energy by moving. In quantum mechanics, energy is not lost by moving. It is stored in the uncertainty of the motion itself. The more confined the electron, the more energetic it must be on average. And that energy is what holds the atom open. Run the Schrödinger equation on hydrogen with these conditions, and it spits out the exact size of the hydrogen atom, accurate to the width of a single proton. The Bohr model estimated the size using a lucky guess. Quantum mechanics derives it from first principles with perfect precision. The same calculation explains why different atoms have different sizes. Heavier nuclei have stronger positive charges. Stronger positive charges pull electrons closer. But the quantum confinement effect scales with the confinement radius, so a stronger pull finds a new balance point closer in, producing a smaller atom. Atoms do not just grow proportionally larger as you add protons. Their sizes are set by the precise balance between electrical attraction and quantum outward pressure, different for every element. The atom is not a fragile solar system on the verge of collapse. It is a finely tuned standoff between two opposing effects, and it holds with extraordinary stability. But the shapes those standoffs create inside the atom are far stranger than anyone expected. Every atom in existence is a battlefield. Two forces locked against each other, neither one winning, holding the structure in place through pure opposition. Pull the nucleus, push the electron's quantum energy. Balance, hold. Repeat across every atom in every molecule, in every object, in the observable universe. The electrical force is the attacker. Opposite charges attract with a strength that follows a precise rule. Double the distance and the force drops to 1/4. Cut the distance in half and the force quadruples. At the tiny scales inside an atom, this force is extraordinarily strong, far stronger than gravity, far stronger than most everyday forces a person can feel or generate. The nucleus, packed with positively charged protons, reaches outward with this force in all directions. Every electron in the atom feels it constantly, being pulled toward the center with a strength that scales with how many protons are in the nucleus. Hydrogen has 1 proton pulling 1 electron. Uranium has 92 protons pulling 92 electrons. The pulling never stops. The quantum outward push is the defender. It has no name as clean as electricity. It is a consequence of the uncertainty principle operating at very small scales. Confine a quantum particle and its energy must rise. The smaller the confinement, the greater the energy rise. That rising energy functions as a physical resistance to further compression. The two effects hit their balance point at a specific distance for each element. That distance is the radius of the atom. At that radius, the energy is at its lowest possible value. Move the electron closer. Quantum energy rises faster than electrical energy drops, and the total energy goes up. Move the electron farther. Electrical energy rises faster than quantum energy drops, and the total energy goes up again. The minimum sits exactly at the equilibrium radius. The atom is sitting at the bottom of an energy valley. Push the electron in any direction away from equilibrium, and the energy rises. Remove whatever pushed it, and the electron returns to the bottom of the valley. The atom is stable in the same way a ball resting at the bottom of a bowl is stable. This picture explains one of the most basic facts in all of chemistry. Atoms prefer to exist in their lowest energy states. They resist being disturbed. They return to equilibrium. They hold their shapes. All of this follows directly from the geometry of that energy valley, created by the competition between electrical attraction and quantum confinement. The tug-of-war also explains why the atom has the specific size it does, and why atoms do not all collapse to the same tiny point under the gravitational pull of the universe. Each element sits at its own balance point, determined by the number of protons pulling against the quantum energy pushing back. Change the number of protons, and you change the balance. Change the balance, and you change the atom. Every element in the periodic table is a different solution to the same equation, a different standoff, a different valley bottom, a different atom size, energy level, and set of chemical behaviors, all arising from the same two opposing forces playing out at different strengths. And the shapes those forces create around the nucleus are genuinely bizarre. The atom rests at the bottom of a valley. That valley is not a physical shape you can see. It is a landscape of energy. At the bottom, the electron sits in its lowest possible state. Stable, not moving toward the nucleus, not drifting away. Disturb it, and the energy rises. Release it, and the energy drops back down to the minimum. This picture is why matter is stable over astronomical timescales. A hydrogen atom that formed in the early universe, roughly 14 billion years ago, still has its electrons sitting at the bottom of that energy valley today. Nothing has dislodged it. Nothing has pushed it in or pulled it out. The valley is deep enough and the equilibrium strong enough that the atom simply holds. The depth of the valley determines how hard it is to strip an electron from an atom. Chemists call this ionization energy. A shallow valley means a loosely held electron, easy to remove. A deep valley means a tightly held electron, extremely difficult to strip away. The noble gases, the column on the far right of the periodic table, sit in the deepest valleys of all. Their electrons are so tightly balanced that they almost never react with other atoms. The alkali metals on the far left sit in the shallowest valleys. Their outermost electrons are barely held. Touch sodium to water, and the reaction is violent because that loosely held electron is nearly free already. The energy landscape makes the chemistry. The valley also has layers. A single atom can hold its electrons at multiple energy levels, each one a step up from the floor of the valley. The first and lowest level is closest to the nucleus. The second is farther out and higher in energy. The third is higher still. Each level holds a fixed number of electrons, determined by the shapes that stable quantum waves can take around the nucleus. The first level holds 2, the second holds 8, the third holds 18. These numbers are not arbitrary. They come directly from solving the Schrödinger equation and counting how many distinct wave shapes fit stably at each energy. When an atom interacts with another atom, the outermost electrons, the ones sitting highest in the valley, are the ones that do the interacting. They are the closest to the rim. They are the easiest to push over. Chemical bonding happens when atoms share or trade these outermost electrons in arrangements that lower the total energy of both atoms combined. Two atoms forming a bond is both of them finding a deeper valley to share. The periodic table is essentially a map of these valleys. Columns group atoms with similar outermost electron arrangements. Elements in the same column react similarly because their outermost electrons occupy equivalent positions in their respective energy landscapes. Every rule of chemistry, every bond, every reaction, every molecule ever assembled, is the universe finding arrangements where the energy sits as low as possible. Atoms bond because the bonded state is a deeper valley than the separate state. Molecules hold together because separating them would require climbing back up the slope. The energy valley is not just an explanation for atomic stability. It is the organizing principle of all chemistry. And inside that valley, at the various energy levels, the electron does not sit in any simple shape. The shapes it actually occupies look like nothing in everyday experience. An electron in an atom does not circle the nucleus. It fills a shape. That shape is called an orbital. Orbitals come in several types, and they get dramatically stranger as the energy level rises. They are not circular paths. They are three-dimensional regions of space where the probability of finding the electron is high. Each orbital has a specific geometry determined by the mathematics of the Schrödinger equation. The lowest energy orbital is a perfect sphere. It surrounds the nucleus like a fuzzy ball, dense with probability near the center, thinning out smoothly in all directions as distance increases. 2 electrons can occupy this spherical shell, one with each spin direction. The first shell of every atom from hydrogen to uranium takes this same simple spherical shape. The second energy level introduces something new. Alongside a larger spherical orbital, 3 new orbitals appear that look completely different. Each one has 2 lobes, like a dumbbell, pointing along one of the 3 axes of space. One dumbbell points left and right, One points forward and backward. One points up and down. The electron in a dumbbell orbital is most likely to be found in one of the two lobes, far from the nucleus, with almost no probability of being found in the gap between the lobes at the center. The center of the dumbbell orbital passes through the nucleus. The electron in this shape has essentially zero probability of being found precisely at the nucleus, even though the nucleus sits right at the midpoint of the two lobes. The third energy level adds 5 more orbital shapes, each one a more complex arrangement of lobes and rings. Some look like 4-leaf clovers. Some resemble a dumbbell wrapped with a ring around the middle. These shapes get complicated fast, and they have to be. Each additional shape has to be mathematically distinct from all the previous ones, arranged in 3-dimensional space, without overlapping the probability density of any earlier orbital. The shapes are not decorative. They directly determine how atoms bond with each other. Carbon, the element that makes up the backbone of every biological molecule, forms 4 bonds. That number comes directly from the number and shape of its available orbitals. When carbon bonds with 4 hydrogen atoms to form methane, the 4 bonds arrange themselves pointing toward the corners of a tetrahedron, a 3-dimensional triangular pyramid. The angle between each bond is about 109 degrees. That specific angle comes from the geometry of the carbon orbitals orienting themselves to minimize their overlap and the repulsion between electrons in different bonds. The shape of the water molecule, with its bent angle of about 104 degrees between the 2 hydrogen atoms, comes from the same orbital geometry. 2 bonding orbitals and 2 lone pair orbitals on the oxygen atom, all pushing away from each other into the positions that minimize total energy. Molecular shape determines molecular behavior. The reason water is a liquid at room temperature, while hydrogen sulfide, a molecule with similar size and mass, is a gas, comes down to the bent geometry of water and how that geometry allows molecules to grab onto each other electrically. The geometry comes from orbitals. Orbitals come from the Schrödinger equation. The Schrödinger equation comes from treating the electron as a wave of probability. Every shape in biochemistry, every protein fold, every enzyme cavity, every strand of genetic material curling into its famous double helix structure traces back to the geometry of electron probability clouds in atoms. And those clouds have one more secret nobody mentions in basic chemistry courses. The spherical orbital around the nucleus is not hollow at the center. For the most energetically stable type of orbital, the probability of finding the electron does not drop to 0 at the nucleus. It reaches a local maximum there. The electron is actually most likely to be found somewhere in a shell around the nucleus, but there is a real, non-zero probability that it exists right inside the nucleus itself, passing through the densest region of positive charge at the heart of the atom. This seems like it should cause exactly the catastrophe that started this whole story. The electron is inside the nucleus. The positive charges are there. Shouldn't it get captured? The answer is no, and the reason is energy. Getting captured inside the nucleus would require the electron to be confined to a space roughly 100,000 times smaller than an atom. Heisenberg's uncertainty principle handles that scenario directly. Squeeze the electron into nuclear dimensions, and its momentum uncertainty explodes. The kinetic energy required to be that confined is vastly larger than the electrical energy gained by sitting close to the protons. The electron passes through the nucleus the way a fast-moving ball passes through a shallow dip in the ground. The dip exists. The ball enters it, but the ball is moving so energetically that the dip cannot hold it. It passes straight through and continues. Scientists confirmed this experimentally through a technique called electron capture spectroscopy. The slight overlap between the electron's probability cloud and the nuclear volume shifts the observed spectral lines of certain atoms by a tiny but measurable amount. The size of that shift tells physicists exactly how much time the electron spends overlapping with the nucleus. The overlap is real and calculable. For certain types of orbitals, the dumbbell-shaped ones, and the more complex higher energy shapes, the probability at the exact center of the atom is zero. The electron cannot be found there. A nodal point, a location of zero probability, sits right at the nucleus for these orbitals. The electron exists in the lobes on either side, never at the center. The lowest energy spherical orbital has no such node at the center. The electron in that state genuinely spends measurable time inside the nuclear volume. This fact has a subtle but real effect on atomic physics. Reactions that depend on nuclear properties, such as the energies of certain radioactive decays, are slightly altered by the presence of electron probability density inside the nucleus. In heavy atoms with many electrons, the innermost electrons spend enough time near the nucleus that their velocity approaches a significant fraction of the speed of light. At those speeds, the equations of special relativity become necessary to correctly describe the electron's behavior. Gold owes its distinctive yellow color partly to this relativistic correction. Without the relativistic mass increase in the inner electrons, gold would be predicted to look silver-white, like most other metals. The electron passing through the nucleus is not just a curiosity. In heavy atoms, it reshapes the entire electronic structure. The electron survives passing through the nucleus every time, ejected by its own kinetic energy, before the electrical attraction can trap it. Under almost all conditions in stable matter, the nucleus cannot hold on. Almost all conditions. There is one specific scenario where the nucleus wins, where the electron does get captured and something deeply strange happens as a result. Niels Bohr made a prediction that seemed physically absurd when he first proposed it. He said electrons do not gradually slide between energy levels. They jump instantly. One moment the electron is at one energy level, the next moment it is at another. No travel time, no path between them, no crossing of the space in between. The electron simply ceases to exist at one level and appears at another. In 1913, this was an assumption Bohr made to fit the data. He had no mechanism for it. He just declared it as a rule because the spectral lines of hydrogen demanded it. If electrons moved gradually between levels, atoms would emit a continuous smear of colors. Instead, they emitted sharp, precise lines. Sharp lines meant discrete jumps. For decades, physicists debated whether the jump was real or just a mathematical convenience. Some believed that quantum mechanics was a statistical description of something smoother happening underneath. Einstein spent years insisting that quantum jumps were a sign that the theory was incomplete. Something continuous had to be going on beneath the surface. In 1986, 3 separate research teams caught a single atom in the act of jumping. They trapped individual atoms and bathed them in laser light tuned to drive electrons between 2 specific energy levels. When the electron was at the lower level, the atom emitted flashes of light continuously. When the electron jumped to the upper level, the flashes stopped completely. The atom went dark. The teams watched atoms blinking on and off, like a tiny switch. Light, dark, light, dark. No gradual fading, no slow transition. Full brightness, then zero, then full brightness again. The switch between states happened in less than any time interval the instruments could resolve. The quantum jump is real. The electron genuinely disappears from one energy level and reappears at another with no detectable travel between them. The duration of the jump, if it has one, is shorter than the smallest time interval ever measured by any instrument ever built. This creates a genuinely strange picture of what happens inside an atom during ordinary light emission. The electron exists in its higher energy state as a spread-out probability cloud. The lower energy state also exists as a spread-out probability cloud of a different shape. At some unpredictable moment, the electron transitions from one cloud to the other. The transition is not gradual. The probability cloud does not slowly shrink on one level and slowly grow on the other. The electron is in one state, and then it is in the other, and the 2 states have no physical overlap in between. But when the electron jumps down, energy has to go somewhere, the atom sheds the energy difference as a photon, a single particle of light. And the energy of that photon, which determines its color, is exactly equal to the gap between the two energy levels, the electron crossed. Precise energy gap, precise color. That is why hydrogen always emits the same specific shades. The gaps between its energy levels are fixed by quantum mechanics. Every hydrogen atom in the universe has the exact same gaps. Every jump between the same two levels releases a photon of exactly the same color, anywhere in the universe at any point in history. The same rule works in reverse. Atoms absorb photons whose energy matches one of their energy gaps, and the electron jumps upward. A photon of the wrong energy gets ignored entirely. This selectivity is why each element has a unique spectral fingerprint, and how scientists identified helium in the sun before anyone ever found it on Earth. The quantum jump was the first hint that the universe at its smallest scale operates in discrete steps with nothing in between, and the light those steps release paints the entire visible world around us. Every color you have ever seen came from an electron dropping to a lower energy level. That is not a poetic statement. It is a literal description of the physical process behind all visible light. The red of a sunset, the blue of the sky, the green of leaves, the glow of a phone screen. Every photon your eye has ever detected was produced when an electron gave up a precise packet of energy and released it as light. The mechanism is always the same. An electron absorbs energy from somewhere, a collision with another atom, heat, an incoming photon, an electrical current. That energy pushes the electron from its current level to a higher one. The higher level is unstable. The electron cannot stay there indefinitely. After a time, typically measured in billionths of a second, it drops back down. The energy difference between the two levels does not vanish. It emerges as a photon whose energy exactly matches the gap the electron crossed. The energy of a photon determines its frequency, and the frequency of light determines its color. Visible light covers a narrow band of frequencies. Photons with slightly too much energy fall in the ultraviolet range, invisible to human eyes, but detectable by instruments and capable of damaging genetic material. Photons with slightly too little energy fall in the infrared range, felt as heat but not seen as color. The specific colors emitted by each element depend entirely on the specific energy gaps in that element's electron structure. Neon produces its orange-red glow because the energy gaps in neon atoms happen to fall in the visible range when electrons jump between certain levels. Sodium produces a sharp yellow-orange color for the same reason. Mercury vapor produces the distinctive blue-white light of older street lamps. Fireworks are a controlled version of this same process. Different metal salts are packed into the shell. When they burn, the heat excites electrons in the metal atoms to higher levels. As those electrons drop back down, they release photons. Strontium compounds produce red, barium produces green. Copper produces blue. The colors are not dyes or pigments. The sun produces white light because it contains so many different elements at such extreme temperatures that millions of different electron transitions occur simultaneously, covering the entire visible spectrum at once. The mix of all those colors together appears white. When sunlight passes through the atmosphere, nitrogen and oxygen molecules scatter shorter wavelengths of light more strongly than longer ones. Blue light scatters in all directions across the sky. Red light travels more directly through. The sky appears blue from the scattered blue photons reaching your eyes from every direction overhead. The sunset appears red because you are looking through a longer path of atmosphere, and most of the blue has already scattered away. Every color in the natural world traces back to quantum mechanics. The green of a leaf comes from chlorophyll molecules whose electron structure absorbs red and blue photons. The blue of the ocean comes from water molecules absorbing red wavelengths slightly more than blue. The brown of wood comes from complex organic molecules with electron arrangements that absorb across the visible range except in the brown frequencies. Color is electron physics made visible. And the same process that paints the world in color also produces the radiation that makes certain atoms dangerous. Because electron transitions are not the only jumps that happen inside atoms. Some atoms have something far more violent occurring at their cores. The person who cracked the connection between electron jumps and color was not looking for color at all. Johann Balmer was a Swiss mathematics teacher in his 60s in 1885. He had no laboratory, no equipment, and no particular expertise in physics. He had a table of numbers representing the wavelengths of 4 visible lines in the hydrogen spectrum: a red line, a blue-green line, a violet line, and a deep violet line at the edge of visibility. Balmer stared at those 4 numbers for weeks and noticed something. They followed a pattern. A simple mathematical relationship connected all 4 wavelengths. He published a formula. It had no theoretical basis. He had no idea why the pattern existed. He just noticed it was there. The formula predicted a 5th line just beyond visible violet. Astronomers checked their existing data on hydrogen in stellar atmospheres and found it, right where Balmer said it would be. They found more lines further into the ultraviolet, all following the same formula. Balmer's formula was a clue with no explanation for 30 years, until Bohr showed that his quantized energy levels produced exactly that mathematical pattern. The gaps between Bohr's energy levels, when converted to photon energies, matched Balmer's formula exactly. The pattern existed because the electron's energy levels were set by quantum rules, and those rules happened to produce gaps that fell in the visible range for certain transitions in hydrogen. The connection between the abstract mathematics of quantum mechanics and the specific colors humans can see is a coincidence of scale. The energy gaps in common atoms often fall in or near the visible range because atoms are the size they are, and atoms are the size they are because of the balance between electrical attraction and quantum confinement. The numbers happen to work out so that many atomic transitions produce light that eyes built from those same atoms can detect. This is the physical story behind every color-based technology humans have built. A laser works by pumping electrons in a specific material to the same excited energy level simultaneously. When they drop back down together, they release photons in perfect synchrony, all the same wavelength, all traveling in the same direction. A coherent beam instead of scattered light. Medical lasers cut tissue because their photons carry exactly the right energy to be absorbed by water molecules in cells. Laser pointers, laser printers, Blu-ray players, fiber optic internet connections. All of them depend on driving electron transitions in precisely chosen materials. Light-emitting diodes, the technology behind almost every screen and lighting device built in the last 2 decades, work by running electrical current through materials where electrons are forced to cross specific energy gaps. Tune the material, and you tune the color. Red, green, and blue light-emitting diodes, combined at varying intensities, produce every color a modern screen can display. Fluorescent materials absorb ultraviolet light, which carries more energy than visible photons, and re-emit it as visible light at lower energy. The material converts invisible radiation into visible color by stepping the electron transitions down through intermediate levels. Laundry detergent uses fluorescent compounds to make white clothes appear brighter than white by adding ultraviolet to visible conversion. The electron's energy levels are the universe's color palette, and the fact that they are discrete, fixed, and identical for every atom of the same element is also the basis of one of the most powerful tools in science, because those fixed color fingerprints let scientists identify atoms anywhere in the universe without ever touching them. Every chapter so far has told the same story. The electron approaches the nucleus, the quantum rules push back, the atom holds, the electron survives. There is an exception. In certain atoms, under specific conditions, the nucleus reaches out and actually captures an inner electron. The electron does fall in. A proton absorbs it, and something genuinely strange exits the atom in its place. The process is called electron capture. It happens in radioactive atoms that have too many protons relative to their neutrons. A nucleus needs a balanced ratio to be stable. Too many protons creates intense internal electrical repulsion. The nucleus wants to reduce its proton count. One way is to grab an inner electron, usually from the lowest energy orbital where the probability of the electron overlapping with the nucleus is highest. When the proton absorbs the electron, the two combine. A proton carries a positive charge, an electron carries an equal negative charge. Together, they cancel. The result is a neutron, electrically neutral. The nucleus gains a neutron and loses a proton. The element changes. An atom with one fewer proton becomes a different element entirely, sitting one step to the left on the periodic table. When this capture happens, a ghost-like particle called a neutrino also exits the nucleus at nearly the speed of light. Neutrinos have almost no mass and interact so weakly with matter that they can pass through the entire planet Earth the way light passes through glass. Roughly 65 billion neutrinos from the Sun pass through every square inch of your body every second at this moment without any effect. You cannot feel them. No instrument has ever stopped one. Scientists detect them only through rare accidental collisions with atomic nuclei in enormous underground tanks. After electron capture, the atom has an empty slot in its lowest energy level. Electrons from higher levels fall down to fill the gap. Each one dropping to a lower level releases a photon in the X-ray range, far more energetic than visible light. Medical X-ray machines do not use electron capture directly, but they exploit the same physics, driving electron transitions in heavy metal atoms to generate high-energy photons that pass through soft tissue while stopping at bone. The atoms that undergo electron capture are all unstable isotopes. They exist in nature as products of radioactive decay chains and can be produced artificially in particle accelerators. Some are used in medical imaging. A radioactive isotope injected into the body undergoes electron capture and emits detectable radiation that scanners pick up from outside, producing images of internal organs without surgery. The fascinating part of electron capture is how it illustrates the limits of quantum protection. The same uncertainty principle that normally shields the electron by making tight confinement energetically costly becomes irrelevant when the nuclear conditions are extreme enough. Enough protons crammed into a nucleus creates enough electrical energy to overcome the quantum resistance. The nucleus turns the electron's own wave function against it, using the finite overlap probability of the lowest orbital as an entry point. Stable atoms are immune. Their proton-to-neutron ratio sits in the comfortable zone where electron capture would cost more energy than the nucleus can supply. The quantum barrier holds. Unstable atoms are a different situation entirely, and the physics of what happens when instability reaches its extreme limit takes the story to somewhere far darker than a simple proton transformation. When electron capture fires a neutrino out of a nucleus, the particle it releases is one of the strangest objects in all of physics. The neutrino has almost no mass. Scientists spent decades assuming it had exactly zero mass. Experiments in the 1990s proved it has a tiny but real mass, smaller than 1/1,000,000th of the electron's mass, which is already incredibly small. The neutrino is so light that it travels at speeds indistinguishable from the speed of light. It carries no electrical charge. This is the root of its ghostly behavior. Almost all interactions between particles happen through electrical forces. Protons and electrons feel each other across vast distances because their charges reach through empty space. A particle with no charge is invisible to those forces. The neutrino also does not respond to the strong nuclear force that holds protons and neutrons together inside the nucleus. It responds only to gravity and to a very weak short-range force called the weak nuclear force. The weak nuclear force has an extraordinarily short range. It only operates across distances smaller than the diameter of a proton. For the neutrino to interact with anything using this force, it has to pass within that tiny range of a nucleus. The chance of this happening as a neutrino travels through ordinary matter is almost impossibly small. To stop half of the neutrinos produced in electron capture with lead shielding, you would need a wall of lead extending from Earth to the nearest star, roughly 4 light-years away. Ordinary shielding is completely useless. The neutrino passes through it as if it were empty space. This creates a serious challenge for physics. Neutrinos carry energy away from nuclear reactions. Stars produce them in staggering numbers during nuclear fusion in their cores. Supernovae release the bulk of their energy as neutrinos in the first 10 seconds of the explosion. But measuring these particles requires detectors of extraordinary size. The largest neutrino detectors humans have built are buried deep underground to shield them from other forms of radiation. One of them, filled with roughly 50,000 tons of ultra-pure water and lined with thousands of sensitive light detectors, managed to catch about 12 neutrinos from a supernova that occurred in a neighboring dwarf galaxy in 1987. 12 detections from a stellar explosion violent enough to briefly outshine an entire galaxy of 100 billion stars. The neutrino's ghostly nature also makes it almost impossible to study its properties directly. Scientists infer its mass not by measuring it directly, but by studying subtle effects in the behavior of other particles during reactions involving neutrinos. The precise value of the neutrino mass remains unknown. Physicists know it is small and real. The exact number has not been pinned down. There are 3 types of neutrinos. One, paired with each of the charged leptons. The electron type emerges from electron capture. As a neutrino travels through space or matter, it can spontaneously change from one type to another, a process called neutrino oscillation. This oscillation was the first experimental proof that neutrinos have any mass at all, because a truly massless particle cannot change type. A particle that passes through planets, travels at nearly the speed of light, changes its identity mid-journey, and barely interacts with anything, is already extraordinary. The neutrino becomes stranger still when you learn that it may be its own antiparticle, a property no other known particle shares. That question remains open, and it may hold the answer to one of the deepest mysteries in cosmology. Not every atom faces the threat of electron capture. The vast majority of atoms in the universe are completely stable and will remain so for longer than any current scientific instrument can measure. The difference between a stable atom and an unstable one comes down to a ratio. Protons and neutrons inside a nucleus interact through the strong nuclear force, the most powerful force in nature, operating at extremely short range to hold the nucleus together against the electrical repulsion of the packed positive charges. The balance between the number of protons and neutrons determines whether this force can maintain stability. Light atoms tend to have roughly equal numbers of protons and neutrons. Carbon has 6 of each, nitrogen has 7 of each, oxygen has 8, 9 or 10 neutrons depending on the isotope, with 8 of each being by far the most common and stable variety. At these low atomic numbers, the equal ratio works well. The strong force handles the repulsion without difficulty. Heavier atoms need more neutrons than protons to stay stable. As you add protons to a nucleus, their combined electrical repulsion grows. More neutrons are needed to dilute the proton density and give the strong force more of a grip. Lead, one of the heaviest stable elements, has 82 protons and typically 126 neutrons. The neutrons outnumber the protons by more than 50%. An unstable nucleus is one where the ratio is off. Too many protons relative to neutrons means the electrical repulsion is winning. Electron capture is one way the nucleus tries to correct this imbalance, converting a proton into a neutron by grabbing an electron. The atom shifts toward a more stable proton-to-neutron ratio and settles. Stable atoms have ratios sitting comfortably in the zone where no such correction is needed. Their electron capture rate is essentially zero. The quantum overlap between the inner electron's wave function and the nuclear volume exists, but the energy ledger does not favor the reaction. The proton has no incentive to absorb the electron because doing so would produce a nucleus with too many neutrons and too few protons, a different kind of instability. Stable atoms are locked into configurations where every possible nuclear transformation would make things worse. They sit at energy minima in nuclear physics, the same way electrons sit at energy minima in atomic physics. Disturb them and they resist. Leave them alone and they hold indefinitely. The most stable nucleus in existence is iron 56, which contains 26 protons and 30 neutrons. Its protons and neutrons are packed together in the tightest, most energetically favorable arrangement that the strong nuclear force allows. No nuclear reaction involving iron 56 releases energy. Every reaction consumes energy instead. Stars produce energy by fusing lighter elements up to iron and by splitting heavier elements down toward iron. Iron is the endpoint, the ash at the bottom of stellar nuclear burning. When a massive star exhausts its fuel and its core becomes iron, the energy production stops. The core collapses under gravity. The collapse compresses the electrons and protons so violently that electron capture occurs on a massive scale, converting the entire iron core into a ball of neutrons in less than 1 second. That collapse is the trigger for the most energetic explosion in the observable universe. The outer layers of the star, hundreds of times more massive than Earth, rebound off the incompressible neutron core and detonate outward at a significant fraction of the speed of light. The star becomes a supernova. Every particle in the Standard Model has been assigned a size. Most of them have measurable radii determined through scattering experiments that send other particles into them and analyze the angles of deflection. Protons have a radius that experiments have measured carefully. Neutrons have a radius. Even composite particles made of quarks have measurable sizes. The electron has a radius too, but the situation with the electron is deeply uncomfortable. Experimentally, the electron's radius is smaller than any distance physicists have ever been able to probe. Every scattering experiment ever performed is consistent with the electron having zero size. A point, a location in space with no extent, no width, no volume. This is where the mathematics becomes a crisis. The electric field of a charged particle contains energy. The field radiates outward from the charge and carries a certain amount of energy per unit volume at each distance. If you want to calculate the total energy stored in the electric field of an electron, you integrate that energy density from infinite distance down to zero, and then you collect contributions from smaller and smaller shells around the charge. For a particle with a real finite size, the integration stops when you reach the surface of the particle. Total field energy, a large but finite number. For a point particle, the integration never stops. The field energy density grows without bound as you approach zero distance. The total field energy of a true point charge is infinite. An electron with infinite field energy would have infinite mass through the famous equivalence of energy and mass. The electron demonstrably has a tiny finite mass. The calculation is broken. Physicists in the 1940s and 50s confronted this problem directly. Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga independently developed a technique called renormalization to handle it. The technique observes that the infinite self-energy can be systematically subtracted from calculations using a set of carefully defined rules, leaving behind finite physically meaningful predictions. Renormalization works. Its predictions match experiments to extraordinary precision. The magnetic moment of the electron, a property related to how strongly it responds to magnetic fields, has been calculated using renormalization to more than 10 significant figures. Experiments have confirmed the result to the same precision. The theory is accurate. But Feynman himself, who won the Nobel Prize for this work, called renormalization a shell game. He wrote that it was a way of sweeping the infinities under the rug without explaining where they came from. The mathematical procedure gives correct answers. The physical understanding of why the electron can have finite mass, despite apparently infinite field energy, remains incomplete. The resolution most physicists accept today is that the point-particle model is an approximation that works at currently accessible energies, but breaks down at some smaller scale not yet reachable by experiment. The electron almost certainly has some structure, some minimum size, below which its behavior changes in a way that removes the infinity. The problem is that the scale where this breakdown occurs, if it exists, is estimated to be so far below any current experimental reach that it may never be directly probed. The electron is the smallest thing physics has ever studied in detail, and the deeper scientists look, the less clearly they can see its edge. The mathematical crisis of the point-particle electron pushed physicists toward a radical alternative. What if particles are not points? What if, at a scale so small it makes an atomic nucleus look like a continent, every fundamental particle is actually a tiny loop of vibrating energy? This is the central idea of string theory. The loop is called a string. At the scales of everyday physics, and even at the scales probed by the most powerful particle accelerators ever built, the string is so impossibly small that it appears to be a point. Every measurement produces results consistent with zero size, because the actual size of the string is far smaller than any probe humans have ever created. But the string is not a point. It vibrates, and the way it vibrates determines what kind of particle it appears to be. A string vibrating in one mode appears as an electron. A string vibrating in a different mode appears as a quark. Another mode produces a photon. The entire zoo of fundamental particles in the Standard Model, plus gravity, would emerge from the same underlying object, expressing different vibrational patterns. This is analogous to a guitar string. Press it at the 12th fret and pluck it. The string vibrates at a certain frequency and produces one note. Press it elsewhere and it produces another. The string is the same physical object. The different vibrations produce different sounds. String theory strings would be approximately 100 billion times smaller than a proton. Expressing this in a human scale, if a proton were expanded to the size of the entire observable universe, roughly 93 billion light-years across, a string would still only be the size of a single tree. That scale is so far beyond any conceivable instrument that testing string theory directly may be permanently impossible. The highest energy particle accelerator ever built would need to be roughly 100 quadrillion times more powerful to probe string-scale physics. No engineer or physicist alive expects that machine to ever exist. String theory does have indirect mathematical support. It naturally incorporates gravity, something the Standard Model cannot do. It eliminates the infinities that plague point-particle calculations, because strings have a real size, and their field energies integrate to finite values. It produces a mathematically consistent framework for describing all known forces in the same language. It also predicts the existence of extra spatial dimensions beyond the three we experience. These extra dimensions would be curled up so tightly at string scale that they are completely invisible to any experiment. Their existence would affect physics only at energies far beyond current reach. String theory has produced an enormous amount of productive mathematics that has influenced other fields, including pure math, condensed matter physics, and black hole thermodynamics. Whether it describes the actual physical universe remains an open question that may stay open for generations. The electron's true structure, if it has one, sits behind a wall that current science cannot see past. String theory offers one possible picture of what is on the other side, but it is one possibility among several, and none of them can currently be tested. What scientists can test, and have confirmed repeatedly, is that the electron behaves as if it has no size down to the smallest distances ever probed. The mystery of its interior, if it has one, is among the deepest open questions in fundamental physics. And that mystery matters far beyond theoretical elegance, because the electron's properties, whatever their ultimate origin, shape everything about the physical world that exists outside a physics laboratory. Building an instrument to see inside an electron would require energy levels that beggar the imagination. The way physicists look inside particles is through collisions. Accelerate particles to high speeds, smash them together, and the energy of the collision probes smaller and smaller scales. Higher energy means shorter wavelength probes, and shorter wavelength means finer resolution. This relationship is a direct consequence of the wave nature of matter. The Large Hadron Collider, outside Geneva, the most powerful particle accelerator ever built, accelerates protons to energies of several trillion electron volts, a unit of energy used in particle physics. At those energies, it can probe structures down to about 1/1000th of a proton's radius. That is an extraordinary achievement, requiring a circular tunnel 17 miles in circumference, superconducting magnets chilled to temperatures colder than deep space, and thousands of scientists working over decades. The scale where quantum field theory is expected to break down, and where the structure of the electron might become visible, is at an energy roughly 100 quadrillion times higher than what the Large Hadron Collider achieves. A machine capable of reaching that energy would, under current technology, require a collider ring roughly the diameter of the Milky Way galaxy, 100,000 light-years across. No civilization is building that machine. There are theoretical proposals for reaching higher energies with more compact technology, plasma-based accelerators, laser-driven methods, exotic field configurations. The most optimistic projections from these approaches might eventually increase collision energies by a factor of 1,000 or 10,000 over current levels. Impressive gains. Still roughly 100 trillion times short of what would be needed. Physicists have developed strategies for working around this barrier. They use the electron's behavior as an indirect probe of its own structure. Any deviation from the predictions of quantum electrodynamics, the most precise theory of electron behavior, would signal that something is happening at scales the theory cannot see. So far, quantum electrodynamics has passed every test. Its predictions match measurements to more decimal places than almost any other comparison in science. This agreement is informative in a specific way. It says that whatever is happening inside the electron, at scales below current resolution, it does not significantly affect the electron's behavior at accessible scales. The electron acts like a perfect point particle, or very close to one, across every distance physicists have been able to examine. Scientists also use theoretical constraints. Any hidden structure inside the electron would have to be consistent with all observed properties. The electron's magnetic moment, its mass, its decay behavior, its interactions with all known forces, every measurement adds a constraint. The space of allowed hidden structures shrinks with each precision measurement. The current constraints place the electron's structure, if any exists, at a size smaller than about 1/10,000th of a proton's radius. Given that a proton is already incomprehensibly small, this limit is almost beyond the capacity of language to convey. The answer to what the electron is made of, if it is made of anything, may require an entirely new kind of physics. One that operates on principles not yet imagined. One that emerges from a breakthrough as unexpected as quantum mechanics itself was to the physicists of 1897. Physics has been surprised before. The electron was surprising. Quantum mechanics was surprising. The surprises tend to come when the gap between prediction and observation grows large enough that the old framework finally cracks. That crack for the electron has not appeared yet, but physicists are watching carefully for it. Every object you have ever held, every surface you have ever pressed your hand against, every time you have picked something up and felt its weight and solidity in your fingers, you did not touch it. The electrons in your skin and the electrons in the object pushed against each other before any atoms made contact. You felt the repulsion. Your brain interpreted the resistance as touch, but the atoms never met. This is not a philosophical point about the nature of reality. It is a precise description of what happened physically. When two electron clouds approach each other, the Pauli exclusion principle and the electrical repulsion between like charges combine to create an extraordinarily strong outward force at short distances. This force grows rapidly as the clouds overlap and reaches magnitudes that feel solid and impenetrable to human senses. The gap between the actual atoms at the moment of apparent contact is roughly 10 to 100 times larger than an atom itself. You and everything you have ever physically interacted with have maintained this atomic scale separation at all times. This has a strange implication for everything around you. The floor you stand on does not hold you up through mechanical contact in any traditional sense. It holds you up because the electron clouds in the molecules of the floor's surface repel the electron clouds in the molecules of your feet strongly enough to counteract the force of gravity. You are levitating at atomic scale above every surface you have ever stood on. The hardness of materials, the reason some objects resist deformation and others yield easily, comes from how tightly packed their electron clouds are and how strongly they resist overlap. A diamond is hard because its carbon atoms are arranged in a lattice where the electron clouds interlock in the most resistant possible configuration. A block of soft clay yields easily because its molecules slide past each other with minimal electron cloud resistance. The sense of touch itself is a measurement of electron cloud repulsion. Pressure receptors in human skin detect deformation caused by that repulsion and send the signal to the brain, which interprets it as texture, temperature, and force. The brain builds a model of the physical world from electron cloud interaction data and presents it to conscious experience as solid objects with surfaces. Sound travels through air as pressure waves, compressions, and expansions of gas molecules. Each compression pushes molecules closer together until their electron clouds resist further approach, then the bounce propagates outward. Electron cloud repulsion is the mechanism of every compression wave, every sound, every vibration transmitted through any solid or liquid medium. Friction is electron cloud interaction between surfaces. Electricity is the directed flow of electrons through a conductor pushed by a voltage difference. Magnetism is produced by the motion and alignment of electrons in materials. Heat in solids is the vibration of atoms, which means the oscillation of electron clouds around nuclei. Every macroscopic physical phenomenon that defines daily human experience, the feel of a surface, the sound of a voice, the warmth of sunlight, the resistance of a wall, can be traced back to what electrons are and what they do. The electron, a particle so small it may have no size at all, is the physical interface between the fundamental quantum world and the solid-seeming reality a person walks through every day, and its effects extend far beyond the surface of any object. Roughly 1,800 miles below the ground you stand on, iron is flowing. The outer core of the Earth is liquid iron and nickel, maintained in a molten state by the intense heat of the planet's interior and by the decay of radioactive elements. This iron is electrically conductive. It moves in complex, swirling patterns driven by heat rising from the inner core and influenced by the planet's rotation. Moving electrically conductive material generates a magnetic field. This is one of the most fundamental rules of electromagnetism, discovered in the 19th century and used in every electrical generator ever built. Spin a coil of copper wire near a magnet, and electrons flow. Force electrons to flow through a wire, and a magnetic field appears around it. The two phenomena are expressions of the same underlying physics. The moving iron in Earth's outer core generates a magnetic field that extends from deep underground out into space, forming a region called the magnetosphere. This field reaches roughly 40,000 miles above the Earth's surface, on the side facing the Sun, and stretches for millions of miles on the side facing away from it, compressed on one side and stretched into a long tail on the other by the solar wind. The solar wind is a continuous stream of charged particles, mostly electrons and protons, constantly blowing outward from the Sun at speeds between 200 and 500 miles per second. Without shielding, this particle stream would strip away the atmosphere over geological timescales and irradiate the surface with enough energy to prevent the chemistry of life. Mars lost most of its magnetic field roughly 4 billion years ago when its core cooled and the flowing current stopped. Without the field, the solar wind gradually eroded the Martian atmosphere. Mars went from a world that almost certainly had liquid water on its surface to the cold, thin-aired desert it is today. Scientists can detect the ongoing atmospheric stripping at Mars using instruments on orbiting spacecraft. Earth's magnetosphere deflects the solar wind around the planet. Charged particles from the Sun follow the field lines, spiraling around them rather than penetrating to the surface. Most get channeled toward the poles, where the field lines converge and particles can enter the atmosphere. The interaction between these particles and atmospheric gases produces the auroras, shimmering curtains of color, visible from high latitudes. During periods of intense solar activity, the Sun can release massive bursts of charged particles, called coronal mass ejections. These events compress the magnetosphere and can push the boundary inward dramatically. The largest such events in recorded history temporarily brought aurora sightings as far south as the Caribbean. More critically, they can induce electrical currents in long conductive structures like power lines and pipelines, disrupting electrical grids and communication systems. The magnetosphere also traps some high-energy charged particles in regions called the Van Allen radiation belts, two donut-shaped zones of intense radiation surrounding Earth. Spacecraft and satellites traveling through these belts must be shielded against the trapped particle radiation. Everything in this chain, the liquid ion currents, the field they generate, the deflection of the atmosphere, traces back to the behavior of electrons. Moving electrons create the field. Deflected electrons define the solar wind. Trapped electrons form the radiation belts. The stability of every living thing on Earth owes something to the physics of a particle so small it may occupy no physical volume at all. Human civilization has been running on electrons for roughly 150 years, and for most of that time, the people building the technology did not understand what electrons actually were at a fundamental level. Thomas Edison built the first practical electrical power systems in the 1880s without any knowledge of quantum mechanics. The engineers who wired cities and built telegraph lines and invented the telephone understood that electricity flowed through wires and could do work. They had mathematical rules describing that flow. They did not need to know that the flowing things were quantum particles, obeying uncertainty principles and existing as probability clouds. This is an extraordinary fact about physics. The deep nature of a phenomenon and the practical control of it can be separated by generations of knowledge. You can build enormously useful systems using the behavior of something you do not understand at its roots. Ohm's law, established in 1827, describes the relationship between voltage, current, and resistance in an electrical circuit with a simple formula. It works. It correctly predicts how electrons will behave in a circuit without any reference to quantum mechanics, probability clouds, or the Pauli exclusion principle. Circuit designers still use it today in the same form Ohm published it. The reason quantum mechanics eventually became necessary for electrical engineering is miniaturization. In a large wire-carrying household current, electrons move through a conductor that is billions of atoms wide. At that scale, quantum effects average out. The statistical behavior of trillions of electrons smooths over the individual weirdness of each one and produces clean, predictable classical results. Shrink the conductor down to a few atoms wide, and classical averaging stops working. Individual quantum events start mattering. An electron tunneling through a barrier it classically could not cross becomes a significant fraction of the total current, rather than a negligible rounding error. Quantum effects dominate. Modern transistors, the basic switching elements in every computer processor, have reached dimensions smaller than 10 nanometers, close to the size of a few dozen atoms. At these scales, engineers must account for quantum mechanical behavior explicitly. Electrons tunnel through insulating layers they should classically be blocked by. Energy levels become discrete and quantized. The classical electrical engineering that built the early technology begins to fail. Quantum effects in transistors, once a nuisance to be minimized, are now being deliberately engineered. Quantum dots, quantum wells, and quantum tunneling devices are designed from the ground up using quantum mechanical principles. Quantum computers, currently in early development, store and process information using quantum states of individual electrons or atoms, rather than classical on-off switches. The shift from classical to quantum electrical engineering is underway now, driven by the physical limits of miniaturization. Engineers have reached the scale where they can no longer afford to be ignorant of what electrons actually are. The quantum reality that physicists uncovered, slowly over a century of careful work, has become an engineering constraint that cannot be engineered around. The century of productive ignorance is ending, and what replaces it will depend on understanding at a fundamental level why the electron behaves the way it does and what it actually is. Physicists spent roughly 3 decades building quantum mechanics without being entirely sure it was correct. The theory made extraordinary predictions. It explained the spectral lines of every element. It gave the exact size of the hydrogen atom. It predicted the behavior of electrons in magnetic fields. Every experimental check passed. But the theory's philosophical implications were so strange: particles without definite locations, jumps with no travel time, identical particles that cannot be distinguished, that many physicists, including some of the theory's own architects, resisted accepting it as a final picture of reality. Einstein spent the last 30 years of his life trying to prove it was incomplete. He designed thought experiments intended to expose contradictions. He argued that the probability clouds could not be the whole story, that hidden variables beneath the quantum surface must determine outcomes that appear random. Quantum mechanics, he insisted, was a useful approximation of something deeper and more orderly. The test that settled the question came in 1982. A French physicist named Alain Aspect and his team performed an experiment that Einstein, with his colleague Boris Podolsky and Nathan Rosen, had designed in 1935 as a thought experiment intended to expose an absurdity in quantum mechanics. The Einstein-Podolsky-Rosen scenario involved creating 2 particles in a linked quantum state, then separating them by a large distance and measuring properties of each. Quantum mechanics predicted that measuring one particle would instantly determine the outcome of measuring the other, regardless of the distance between them. Einstein found this conclusion absurd. He called it spooky action at a distance and argued it proved quantum mechanics was missing something. He believed hidden properties carried by each particle from the moment they were created must determine the measurement outcomes, making the apparent instant connection an illusion. Aspect's team created pairs of photons in linked quantum states, sent them to detectors separated by enough distance that no signal traveling at the speed of light could connect them during the measurement. They measured the correlations between outcomes on both sides and compared the result to the mathematical limit that any hidden variable theory could possibly produce. The correlations exceeded that limit. The results matched quantum mechanics exactly and ruled out hidden variables. The particles were genuinely linked in a way that classical physics cannot accommodate. Measuring one instantly affected the outcome for the other, not through any signal crossing the space between them, but through the quantum entanglement connecting their states. Einstein was wrong about this, and the experiment confirmed it with enough precision that no alternate interpretation within classical physics survived. The result did not trouble most physicists the way it troubled Einstein. By 1982, a generation had grown up using quantum mechanics daily and accepting its strangeness as simply the way the world works at small scales. The confirmation of entanglement felt less like a surprise and more like the closing of a debate that should have ended sooner. Quantum mechanics was correct. The electron's probability cloud was not hiding a hidden trajectory. The uncertainty was not a gap in knowledge. It was a feature of reality. And that reality, strange as it is, turns out to be far more useful than the orderly classical world that preceded it. The electron as a particle was already strange enough. Quantum field theory made it stranger. In the 1940s, physicists began developing a framework that combined quantum mechanics with special relativity, the theory describing how space and time behave at extreme speeds and energies. Merging the two required abandoning the idea of particles as fundamental objects entirely. The new framework, quantum field theory, starts from a different foundation. Space is not empty. Every point in space carries a value for every fundamental field: the electron field, the photon field, the quark field, the field associated with every known particle type. These fields fill all of space at all times. They interact with each other. They fluctuate even in their lowest energy states, in what physicists call the vacuum. The vacuum of quantum field theory is not empty. It is a seething collection of fields in their ground states, with quantum fluctuations constantly producing and destroying pairs of virtual particles across all of space. A virtual electron-positron pair can appear from nothing, exist for an unimaginably brief time, and annihilate back to nothing, all within the limits allowed by the uncertainty principle applied to energy and time. These virtual particles are not fiction. They have measurable effects. The energy levels of hydrogen are shifted by a tiny amount compared to what simple quantum mechanics predicts, because the real electron interacts constantly with the virtual particles popping in and out of existence around it. This shift, called the Lamb shift, was measured in 1947 and matched the quantum field theory calculation exactly. The Casimir effect is another measurable consequence. Place two uncharged metal plates extremely close together, within a tiny fraction of a millimeter, and they attract each other. The attraction arises because the space between the plates restricts which virtual particle fluctuations can occur there, while the space outside the plates has no such restriction. The imbalance in vacuum energy pushes the plates together. This force has been measured and confirmed. In quantum field theory, the electron you encounter in an experiment is not a pristine, isolated point. It is a bare electron surrounded by a cloud of virtual particles that constantly interact with it, dressing it in additional properties. The mass of the real electron includes contributions from these virtual interactions. The charge of the real electron is partly screened by the virtual particle cloud. Renormalization, the mathematical technique discussed earlier, is the procedure for correctly accounting for these dressing effects. The electron field interpretation also explains why electrons are indistinguishable. Two electrons are identical because they are both excitations of the same field. A ripple in the Pacific Ocean and a ripple in the Atlantic Ocean are both water waves. Their individual histories are different, but their natures are the same, determined entirely by the properties of water. Two electrons have identical natures because they are both determined entirely by the properties of the electron field, which is a single thing with fixed universal properties. Quantum field theory turned out to be far more than an extension of quantum mechanics. It became the language in which the standard model of particle physics is written. It provided the framework for understanding all fundamental forces except gravity. It produced the most precisely tested predictions in the history of science. And it drew a picture of the electron that would have been completely unrecognizable to the physicists of 1897 who first found it. A particle that is a ripple in a universal field, dressed in virtual particles, stabilized by uncertainty, holding together atoms through quantum confinement, painting the world in color with its energy jumps, and building a magnetic shield around the planet with its collective motion. The electron's size, or the absence of it, is one of the deepest unresolved problems in all of physics. Every other fundamental particle in the standard model falls into one of two categories. Composite particles like protons and neutrons have measurable sizes determined by the arrangement of their internal components. Particles like photons and gluons, the carriers of forces, have no concept of size in the ordinary sense because they have no mass and travel at the speed of light. The electron is in neither category. It has mass. It is not a force carrier. It is classified as elementary, meaning it has no known internal components. And yet experiments find no evidence of any spatial extent. Physicists define an experimental upper limit on the electron's size every time a new higher energy experiment is performed and finds no internal structure. The upper limit on the electron's radius shrinks. Further, the current limit places the electron's radius, if it has one, below about 1/1000th of a proton's radius. The proton's radius is roughly 8-10 trillionths of an inch. 1,000th of that is a scale so small it dissolves into conceptual abstraction. The theoretical side of the problem is equally uncomfortable. Quantum electrodynamics, the theory describing how electrons interact with light and magnetic fields, mathematically assumes the electron is a point particle with zero size. This assumption produces predictions that match experiments to extraordinary precision, but treating mass and charge as concentrated at a geometric point generates infinities that require renormalization to manage. Renormalization works computationally. It removes the infinities and produces finite, correct answers. But it does not explain what physically prevents the electron's field energy from actually becoming infinite. It is a mathematical procedure without a physical story behind it. Several theoretical frameworks propose possible resolutions. Supersymmetry, a theory that pairs every known particle with a heavier partner particle, modifies the behavior of quantum field theory at high energies in ways that might tame the infinities more naturally. It also potentially explains the large difference in mass between the electron and the Higgs boson, which quantum field theory predicts should be nearly the same without careful tuning. Supersymmetric partner particles have been searched for extensively at the Large Hadron Collider and have not been found in any mass range the collider can currently probe. Preon models propose that the electron is actually a composite particle built from even more fundamental constituents called preons. If preons exist and are tightly bound inside the electron, they could give the electron its mass without visible internal structure at currently accessible energies. Preon models face significant theoretical challenges, and no experimental evidence supports them. The Planck scale, an energy and length defined by combining the constants of gravity, quantum mechanics, and the speed of light, is widely regarded as the scale at which quantum mechanics and gravity must be reconciled into a unified theory. At the Planck length, space-time itself may have structure or graininess that changes the rules for point particles. The electron's true nature may only become clear in a theory that successfully merges quantum mechanics and gravity. That theory does not yet exist. Physicists have been working toward it for nearly a century. String theory is the leading candidate, but remains unconfirmed. Loop quantum gravity offers an alternative approach. Several other frameworks have been proposed and partially developed. The electron's size question may be answered only when a complete quantum theory of gravity is finally achieved. Until then, it remains one of the most precisely studied and least understood aspects of fundamental physics. Start from scratch. Build a universe. Fill it with protons. Protons carry positive charge. Pack them together and they repel each other violently. The strong nuclear force can overcome that repulsion at extremely short range, binding protons and neutrons into nuclei. But the nucleus is tiny. Outside the nucleus, the positive charge of the proton radiates its electric field outward into space, seeking something to balance it. Now add electrons. Each one carries negative charge exactly matching a proton's positive charge. Each one is light enough to be held loosely, spread into a probability cloud across a region of space 100,000 times wider than the nucleus. Each one is stabilized by the uncertainty principle so it cannot fall in and annihilate the structure. Each one settles into specific orbital shapes determined by quantum mechanics. creating a defined chemistry of interaction with other atoms. The electron does not just neutralize the proton's charge, it structures the space around the atom into a precise, chemically reactive surface. The arrangement of electron orbitals determines which other atoms an atom can bond with, at what angles, with what strength, in what geometry. Carbon gets its 4 bonds, oxygen gets its 2 bonds and 2 lone pairs. Hydrogen gets its single bond. Every molecular structure in existence is electron orbital geometry, expressed as chemistry. Add enough atoms together, and the electron orbital interactions become covalent bonds, ionic bonds, metallic bonds, hydrogen bonds, and van der Waals forces. Molecules form. Some molecules form chains. Some chains fold into specific 3-dimensional shapes, determined by the geometry of their electron clouds. Some of those shapes turn out to be capable of catalyzing chemical reactions. Some catalysts become capable of self-replication. The chemistry of life begins as electron physics at atomic scale. Every protein in a living cell holds its shape through electron interactions. Every enzyme catalyzes its reaction by bringing electron-rich regions of one molecule near electron-poor regions of another. Every strand of genetic material stores information in the specific sequence of molecular units whose shapes are governed by electron orbital geometry. The reading, copying, and translating of genetic information all happen through electron-mediated molecular recognition events. Beyond biology, electrons hold matter together mechanically. The rigidity of solids, the flow of liquids, the mixing of gases all emerge from electron cloud interactions between atoms. The structure of every crystal, every polymer, every ceramic, every alloy is an expression of how electrons in those materials arrange themselves to minimize energy. Electrons in motion generate every magnetic field in nature, from the weak field of a refrigerator magnet to the titanic field of a neutron star, millions of times stronger than anything producible on Earth. They carry every electrical signal that has ever been transmitted through a wire or a fiber optic cable. They generate and absorb every photon of electromagnetic radiation, from radio waves to gamma rays, making possible every form of communication, every telescope observation ever made. The electron is the interface between the quantum world and the physical world. It is the mechanism through which quantum rules produce observable chemistry, observable physics, observable reality. At the deepest level of what physics currently understands, the electron may have no size. It may be a vibration of a universal field. It may be connected to every other electron in the universe through quantum entanglement and the indistinguishability of identical particles. It has never been broken, never been divided, never decayed. It has existed since before the first star switched on and will continue to exist, as far as any current physics predicts, until the last cold remnant of matter in a dying universe finally goes dark. The smallest confirmed piece of matter in existence turns out to be the reason anything in the universe holds together at all.